Hello everyone, this is going to be a video for engineering statics, where in this video 1 of 2 we'll be covering the first moment of area and also getting into the centroid. Now, looking at a centroid, that's sort of like the two-dimensional version of center of mass for a 3D object, where for centroids, those are going to have a coordinate along that 2D surface, which we'll call that x bar and y bar. And if the structure is present in a uniform gravitational field and density is constant, then essentially what we'll have is the centroid can also be looked at as the center of gravity, which that'll be important. That'll be useful in our second video. So let's say we had two functions where our top function is f of x and our bottom function is g of x. Well, between those two functions, we could calculate the area A as the integral from A to B of dA, which if we convert that into x coordinates, that's basically going to be the integral from A to B of our top function minus our bottom function dx. And while that's cool, the first moment of area, that is called the statical. And that's going to be our qy and qx. Essentially, how does the area between our two curves or our defined shape, how does the area get distributed along the x and y axis? So qy, statical y, that is going to be the integral from a to b of x dA. And in order to solve for that, that would be the integral from a to b of x times the quantity of our top function minus our bottom function, or f of x minus g of x. Whereas the statical qx, that would be the integral a to b of y dA. How does the area distribute around the y-axis? And the integral from a to b would be 1/2 f of x squared minus g of x squared, all that in parentheses multiplied by 1/2. A common error that happens in these types of problems is that some of my past students, when they put in the square, they did not square both the top and bottom function, but left it in the outside of the parentheses. That's just something to avoid. And then if we pull all these together, to get our centroid coordinates, we actually take the solutions to the first moment of area, qy and qx, and we just divide them by the area that we calculated through our first integral. So in reality, x bar is the integral used for qy divided by the integral for area, while y bar is the integral for qx, statical x, divided by the area. And, well, we're going to just solve for that. And once you solve for your centroid, you'll get an x value and a y value. And essentially that literally will be our center of area. And we could put in a little coordinate, for example, like right here, wherever we would get our coordinate system to be. So just as an example, let's say we had the following two functions. Our top function f of x is the square root of x, and our bottom function g of x is x cubed. It doesn't matter if these span multiple quadrants. Really, all that we're looking for is, let's say we have some structure that fits those two curves and is described as the area in between those two curves. And while it's not necessary for us to take the integral from a point where both of those curves meet to the very next point where they meet, sometimes you might have an open end on one of those sides or both. For these problems, we're going to be practicing going from a completely enclosed surface. So for our first mode of area, first thing we're going to want is to calculate the actual area, and that's just the integral from our x coordinates of our x points of interest, in this case from 0 to 1, taking our top function, the square root of x, minus our bottom function, x cubed, dx. After we take the integral, that would just be x to the 3 halves times 2/3 minus x to the 4th divided by 4 from 0 to 1. That becomes 2/3 minus 1/4 minus 0 minus 0. And that eventually gives us the area, 5/12. And if we were doing these in units, you would usually see these in some unit of measurement squared, usually meters squared or inches squared, but that would be for area. As we calculate the x-coordinate of our centroid, what we really just need is 1 over the area times our qy statical integral. So 1 over the area times the integral from 0 to 1 of x times the quantity of square root of x minus x cubed. Essentially taking our top function and bottom function, taking the difference of those two, and multiplying by x. Well, something I like to do is just multiply that x across if it's simple enough to do. And what we would have is the integral of x to the 3 halves minus x to the 4th. And that's simple to do using the power rule. We're going to have 1 over our area, so 1 over 5/12 becomes 12/5 multiplied by the quantity of 2/5 times x to the 5 halves minus x to the 5th over 5. Going from 0 to 1, that's going to give us, just ignoring the side that's just going to be 0, that'll be 12/5 times the quantity of 2/5 minus 1/5. And overall, that comes out to an exact value of 12/25. And just to help us visualize where on our graph that's going to be, that's approximately 0.48. Now, to complete our centroid coordinate, we need the y-coordinate, or y-bar, and that's just going to be 1 over the area times the integral, in this particular case, from 0 to 1, of 1/2 times the quantity of the top function squared minus the bottom function squared. With that 1/2 being a constant, we can take that out of the integral, so that we have 1 over 2 times the area, all in the denominator, times the integral from 0 to 1 of x minus x to the 6th power. What we then have is taking the inverse of our area, 12/5 times 1/2, times the quantity x squared over 2 minus x to the 7th over 7, going from 0 to 1. Our non-zero numbers are going to be 6/5 multiplied by 1/2 minus 1/7, and that all equals the exact value of 3/7, which is approximately 0.43. So for these problems in my class, I'm going to ask you to give the centroid as a coordinate, essentially have parentheses x bar, y bar equal to, and then you can put the exact answer. Or if you want, you can also put in the approximate answer. Use the approximate answer if you're asked to graph that centroid point, just to help you know where that goes. So our exact centroid values, x bar, y bar, are 12/5 and then 3/7, which to visualize that would be 0.48 on the x-axis. So going along our x-axis at about 0.48, and then going up to about 0.43, that is our center of area. And if this structure is in a uniform gravitational field, that is also our center of gravity. And if density is completely uniform throughout, then that happens to be our center of mass as well. Doing a different example. So beforehand, the graph was made just through Google search. This graph right here was made through Wolfram Alpha, or an online graphing program. The online graphing program that was called Mathway. Pretty easy, uses the same programming, I think, as Wolfram Alpha, or maybe ChatGPT, actually. In any case, using Mathway, that's how we get the graph on the left. that is going to be f of x equaling x squared, and our bottom curve between the points 0 to 2, that would be g of x equaling 1/2 times x to the third. And at this point, as always, likes and subscribes are non-necessary, but they are appreciated, and perhaps they'll help the channel grow somewhere pretty cool someday. So if you'd like, please like the video and subscribe. And you know what, if you want to leave a comment, I'd be down to read those and reply to those as well. Calculating our area, that's going to be from the integral from 0 to 2, if we're just looking at the enclosed space, of our top function x squared minus our bottom function 1/2 x cubed. And that's easy enough. That just becomes x to the third over 3 minus x to the fourth over 8, going from 0 to 2. Plugging in our values of 2 and 0. That'll be 8/3 minus 16/3. That quantity minus the quantity of 0 minus 0. And everything eventually simplifies to 2/3 for our area. One thing I should say is that as you're solving these unit analyses type problems, whenever you solve for the statical qy or qx, your units would be a unit of length, whether that's meters or inches, however you measure length in that direction. As we solve for area, that would be length squared, so meters squared, feet squared, inches squared. As we solve for the centroid, that would actually be length cubed, if you ever put that into units. So meters cubed or inches cubed, centimeters cubed, feet cubed. And essentially solving for x bar now, what we have is 1 over the area, integral of 0 to 2 of x times the quantity of x squared minus 1/2 of x cubed. I tried to make these problems so that it's simple enough to plug the x in without needing some integral skills beyond Calculus 2. Essentially, these classes are made, this statistics course is made assuming that you've either had Calculus 2 in college yet, or you're currently taking Calculus 2 as a co-requisite. Distributing that x across, we get the integral of x cubed minus 1/2 x to the fourth, and then solving that gets us 3/2 times the quantity x to the fourth over 4 minus x to the fifth over 10 from the values of 0 to 2. Or 3/2 times the quantity of 16/4 or 4 minus 32 over 10 or 3.2. That gives us, initially, when I did this by hand, I got the value 24 over 20th, which simplifying that's 6/5. And since that gives us an exact value that's easy to write as a decimal, you can also just write 1.2. Y bar, well, that's going to be 1 over the area from 0 to 2 of 1/2 times the quantity of x squared minus the quantity 1/2 of x cubed squared, and then taking the integral of that. First simplifying what's being squared, that gets us x to the fourth minus x to the sixth over 4. Plugging in everything we need, we'll get 3/2, the inverse of area, times 1/2, times the quantity x to the fifth over 5 minus x to the seventh over 28, or 4 times 7. From the range 0 to 2, that gets us 3/4 times the quantity of 32/5 minus 128 over 28. That gives us the exact value of 48 over 35, which, to visualize that would be approximately 1.37 units cubed, whatever unit of length we're using. And then we would just use that to solve for our actual centroid. And if you look at the graph on the left, essentially what we have is we can plug in our centroid coordinate at about 1.2 on the x-axis and 1.37 on the y-axis. So just a little bit below what our top function would equal at 6/5. The exact value, I believe, is 1.44. So we're still inside that closed area. You will have some centroids that are not necessarily, well, sometimes depending on what center we're talking about, it might not actually be within the closed area. But right now, our center of area, not center of mass or center of gravity, but our center of area, is still within our closed space between our curves. Now then, another graph that was made using Mathway. That is going to be our top function is the curve 5x minus x squared, and our bottom function is just the function x. Here we're interested in the values from 0 to 4. So again, where those two functions end up equaling the same value, which you might get some problems where you go from a range of x values where those two functions don't meet at the same value at both ends. That's okay. We would still calculate our centroid, our center of area, the same way. Well, the area in this case from 0 to 4 of 5x minus x squared, the top function, minus the bottom function x. Well, simplifying that would be 4x minus x squared. Be careful when you have a polynomial. For example, if that 5x minus x squared was the bottom function, that would become minus 5x plus x squared as you subtracted the whole thing. Just be careful for things like that. But going back to our actual problem, as we take the integral from 0 to 4, that becomes 2x squared minus x cubed over 3, which that goes to 32 minus 64 over 3, minus the quantity of 0 minus 0. And that exactly equals 32 over 3. Solving for our x bar coordinate, we're going to get x times the quantity, 5x minus x squared minus 4, which we already know the things in parentheses are just 4x minus x squared. So as we multiply the inside by that outer x, we get the integral of 4x squared minus x cubed, which that just becomes 3 over 32nd, the inverse of area, times the quantity of 4/3 x to the third minus x to the fourth over 4. Going from 0 to 4, what we have is 3/32 times the quantity of 256 thirds minus 256 fourths, which, despite there being quite a bit of fractions in there, that actually equals the exact value of 2. And for my class, I like to, just by habit, have at least one decimal place, sometimes 2 decimal places. If it's just the value of 2, you could write the whole number 2. That's just fine. But going on to the y-bar coordinate, remember, whenever you're solving the y coordinate of our centroid, you must be careful to square the top function and the bottom function separately and then take their difference. Also, remember to add in the 1/2 that we're multiplying by. That's necessary to convert these from, instead of using an integral going from a y coordinate to a y coordinate, we can instead just convert everything to just using the same x coordinates, going from an x value to another x value, and solving an integral in terms of x instead of in terms of y. Well, as we square the top and bottom function, we'll get 25x squared minus 10x cubed. And then we'll get plus x to the fourth. and all that is going to be subtracted by x squared. That eventually simplifies to just 24x squared, taking 25x squared minus x squared. That becomes 24x squared minus 10x cubed plus x to the fourth. And solving that integral, we have 3/32 times 1/2 times 8x cubed minus 5 halves x to the fourth plus x to the 5/5 from 0 to 4. That would be 3/64 times the quantity of 512 minus 640 plus 204.8, which, oddly enough, gives us the exact value of 3.6. Again, your units would be some unit of length cubed whenever we're solving for x bar or y bar. Now that we have the exact coordinates, we don't need to use an approximate sign. You could just use the exact values, setting the centroid x bar y bar equal to the coordinate 2, 3.6. And plugging that into our graph, if you're asked to do so, just look for 2 on the x-axis, and then go up to roughly where you would see 3.6 for the y-axis. And if we look at our shape, that makes sense. That our centroid or center of area, it looks like a lot of that area is roughly distributed in the center that we can visualize. In any case, that concludes our first lesson on the first moment of area and the centroid used in engineering statics. One last recap. Our units of measure are going to be the statical QY and QX are always in units of measurement, like meters or inches, and solving for the area, that would be unit of length squared, and then solving for the centroid, that would be units of length cubed. And remember, just one common source of error. X bar is the QY statical divided by area, while Y bar is the QX statical divided by area. And for Y bar, remember to square the top and bottom functions separately before taking the difference, multiply by 1/2, and then multiply by the inverse of area. Whereas for X bar, remember to multiply by the inverse of area and multiply that x across the difference of the top and the bottom function. In any case, that concludes this video. Pleasure to have you all. A like and subscribe and a comment. Not necessary, but certainly appreciated. Let's see where this channel will actually go. And, well, glad to have you all watching the video. And peace.